Hey, all right, so this is part 2 of our video series on intermolecular forces. We're going to be able to rank those forms of intermolecular forces based on the force of attraction between molecules and describe real-world implications. So previously I described ion-ion interaction and ion-dipole interaction. Now we're going to talk about dipole-dipole interaction. In our two videos to follow, we'll go over dipole-induced dipole and dispersion. So dipole-dipole interaction is the interaction between two polar substances that have dipoles. A dipole is defined as two poles, a positive end and a negative end. And so basically when you have two polar substances, they're attracted to each other because those positive and negative ends line up. So examples of that would be sugar dissolved in water. Sugar molecules are polar. Water molecules are polar, and so water molecules will surround the sugar molecules and begin pulling them off of the sugar crystal and dissolving them into solution. It's incredible how much sugar can dissolve into water. In fact, you can dissolve more sugar into water than you have water. Pretty crazy. 120 grams of sugar can dissolve into 100 grams of water. Any polar substance should be able to dissolve in any other polar substance. So let's look at another example. Ethanol is less polar than water, and that's because ethanol has this non-polar end sitting over here, but it does have a polar end, and that means water molecules can attach right here, and they can attach right here. And so ethanol dissolves in water. In fact, you can dissolve any quantity of ethanol into any quantity of water because they're both liquids. You can go anywhere from 95% ethanol and 5% water all the way down to, a drop of ethanol into water. They intermix with each other quite readily and quite easily. Okay, now within dipole-dipole interaction, we have a extra form of intermolecular force, and that's called hydrogen bonding. Hydrogen bonding really is dipole-dipole interaction, but it gets a special name because it's a particularly strong form of it. And it's called that because essentially it is the interaction of hydrogens that are positive with highly electronegative atoms from another molecule. And so, for instance, if a hydrogen from one molecule interacts with an oxygen that's polar from another molecule, you'll have an OH interaction. We represent this hydrogen bond with these dashed lines. So these are not true chemical bonds. Rather, they are strong dipole-dipole interactions where one molecule is interacting with another. Other highly electronegative atoms that can form hydrogen bonds are fluorine and hydrogen and nitrogen and hydrogen. Now, fluorine's not all that common in the environment, and so really, when we talk hydrogen bonds, we're mostly talking about oxygen-hydrogen and sometimes nitrogen-hydrogen. So water hydrogen bonds with itself, where you've got a hydrogen on one water molecule interacting with the oxygen from another. So the interaction that water molecules have with each other is one of the stronger forms of intermolecular forces that's out there, which gives water some really unique and important properties that affect all sorts of issues with biology and chemistry and so forth. So, in fact, hydrogen bonding is the key to life because hydrogen bonding is what holds everything together. It holds proteins together to form the unique shapes that they need for their biological function. It holds DNA together in that double helix to allow for the storing of our genetic material. So here you can see this is a protein sheet where you've got one chain here, these zigzaggy things you see are carbon chains with some nitrogens intermixed. You've got another one here, and you've got another one here, and these can be held together as a sheet by the hydrogen from one hydrogen bonding with the oxygen from another. And it goes down in a repeating pattern. On the opposite side, you've got a repeating pattern. And so this repeating pattern allows these long chains to then line up and form a sheet. Hydrogen bonding is critical to so many different processes biologically. So for instance, let's look at what happens on a DNA molecule. So DNA has got that famous double helix. And really, in many ways, the double helix is simply two molecules, two chains, that are then wrapped around each other and held into place by hydrogen bonding. So in this case, we have A's are attracted to T's and G's are attracted to C's. And you get all of the DNA code comes down to these four molecules: thymine, adenine, cytosine, and guanine. If you look at it at the molecular level, what you'll see is that the oxygen from this thymine is attracted to the hydrogen here on adenine, while the hydrogen on the thymine is attracted to the nitrogen. So there are two hydrogen bonds that hold the A and the T together. In the case of cytosine and guanine, you end up with three hydrogen bonds: hydrogen to oxygen, nitrogen to hydrogen, oxygen to hydrogen. And so it's these hydrogen bonds that hold that double helix in place and hold your DNA together. Now, what ends up happening when you cook food is that you are adding energy to the system and causing the molecules to vibrate rapidly, and that can break the hydrogen bonds. That can cause the proteins and other molecules to unravel from each other. If you add enough energy to the system and these atoms vibrate enough, that hydrogen bond interaction will be overcome and the thing will peel apart and unravel. And that's what makes cooking so useful for eating, because as we break these proteins down, we can change their molecular structure and change that geometry and actually soften it up and make it easier for us to chew it and to digest it. So let's take a look at an example of some what we call denaturing of proteins. Denaturing is the unraveling of all these hydrogen bonds. So when you cook an egg, that white stuff, the white of the egg, is mostly protein dissolved in water. And so when you begin heating it, the proteins begin denaturing, and they start unraveling, and they basically change what they look like. They change their form. We're not changing the molecule exactly. We're changing how they're sticking to each other and how they're interacting. And this denaturing of the protein changes the structure, changes the texture, can even change the flavor. Just some other examples of denaturing of proteins. There are, in some countries, especially in Asia, some other ways to prepare eggs. For instance, these are called century eggs, and what they do in century eggs is that they soak them in lye, which is a basic compound, sodium hydroxide, and they soak them not for a century, but usually for a few months. And during that process, the basic substances come in and change the properties, change the arrangement, the hydrogen bonding of the proteins that made up the egg, and they cause them to become this like jelly-like substance. You can see the color has changed, and that is considered a delicacy in several Asian countries. In certain places, they actually soak them in urine. Yes, I know, tasty, huh? They actually will boil the eggs in urine, and it's those proteins in the urine plus the boiling process that denatures the proteins and forces them to take on a different structure and flavor. I've never tried either of these. I'll let you go and check them out yourself. All right, so denaturing proteins is a very important thing, but it also can be very dangerous. So heating up molecules disrupts the intermolecular forces that are holding them together, and when these proteins unravel, they are no longer able to function properly. And you can see on here the denaturing. So this is the normal structure that protein should have. You notice it's got these different curls and shapes and wrapping around, and it's all held together by intermolecular forces, by hydrogen bonding. When you heat it up, that unravels, and now it can't function the way it normally should. So we actually can use it to our advantage up to a certain point. So if you get sick and you develop a fever, what is going on there is that your body is trying to denature the proteins that are in bacteria or viruses that are infecting you. Your body temperature will rise up several degrees, and basically what you're trying to do is heat up those proteins, cause them to denature, and to kill off the bacteria or make the viruses no longer function properly, and you're trying to kill them before they kill you. And usually it works. If you raise your body temperature up to, say, 100, 101 degrees, just 2 or 3 degrees higher than your normal body temperature, those proteins will begin to unravel, and usually that is an effective tool for killing off invaders. However, it only works to a certain degree. You're fine until your temperature rises to about 104. At 104, your proteins begin to denature, and then it goes from killing off the bacteria to actually killing your own cells. If your temperature rises above 104 and stays there at that level for a certain amount of time, you will begin denaturing your proteins and your organs will begin to fail. At a certain point, you will need to be rushed into the hospital and put onto special cooling devices like this water cooling system here, where basically they're trying to remove the heat from your body and lower your core body temperature and stop that denaturing process. At 108 degrees Fahrenheit, you die. At 108 degrees, all your proteins begin denaturing at such a rate that basically you will die. That term heat stroke, that basically is the situation where your body has reached a temperature, an internal core temperature so high that proteins begin denaturing, processes begin slowing down or stopping, organs begin failing. Every once in a while you hear stories about people hiking in the desert of Arizona in the middle of the summer on a 110-degree day and then dying of heat stroke. Not a good idea. All right, so these polar molecules are going to line themselves up in a crystalline structure. And so here you can see in the solid form, these guys line up in readily available patterns where the negative sides line up with the positive sides in a repeating pattern that essentially forms a crystalline structure. Even in the liquid, they form what's known as a liquid crystal. The water molecules, or whatever the polar molecule is, starts lining up in these, they're liquid, so they're free to move around, but they're constantly shifting their position, trying to line up their positive and negative ends. And if one moves, it's going to force the other to try to move too, to adjust to that. If they get into repulsive position, one's going to rotate. And so water even maintains this crystalline structure in the liquid form in what we call the liquid crystal, except the molecules are shifting a lot more than they are in the solid stage. This regular crystalline pattern that can form when you have a solid is unique to each molecule and its geometry. In the case of water molecules always line up in a hexagonal pattern, a hexagon, in their crystalline form in what we call ice. So here you can see what the water molecules are looking like as they line themselves up. And so you can see that the water molecules are lining up positive to negative, and then over here positive to negative, and then positive to negative, and then positive to negative, and it forms this nice hexagon. It's a repeating pattern of hexagons in all directions. That's how ice forms. And one of the best ways to see this hexagonal pattern for the way these guys line up in the solid stage is to look at a snowflake. A snowflake forms as repeating hexagons going on over, and so you can see on here you've got this hexagon in the middle, and then you've got this hexagon right here, and then you've got this larger hexagon right here, and then even the arms of a snowflake are more ice forming at the point of each hexagon. And so you've got hexagons forming on hexagons and forming on hexagons, and it grows out. All snowflakes form originally as 6-sided crystals with arms that go off in 6 directions, and then arms can come off of those, and arms can come off of those, but it's a repeating pattern of hexagons at every scale.